Good morning, students. Happy Friday. For class today, you are going to need a way to take your electromagnetic spectrum notes. So if you print them out, that is fine. Just be sure that you have a pen or a pencil ready. If you are going to take your notes digitally, I would recommend that you create a split screen if at all possible, and have this PowerPoint on one side and have your notes open in the other. Friendly reminder that if you did not submit your cosmic address video, you need to pause and go do that right now. So the electromagnetic spectrum. Where does all the light in our solar system come from? If you said the sun, you are correct. But besides the light that we are able to see, the sun gives off other types of radiation. And what I want you to notice in this early slide is that anything that I have bolded and underlined in red is something that you need to include in your notes. So using different types of cameras, we can actually see that the sun gives off a lot more radiation than just the light that we see. So these images are from the SOHO Observatory, SOHO. And the only one that is visible light is this orange one that's down in the bottom left. There are, I believe, the blue. I'm not sure what the blue is. Actually, I've forgotten what they all are except for the visible light. So electromagnetic radiation. All of the energy that is produced by the sun is referred to as electromagnetic radiation. And it comes from the nuclear fusion that is occurring in the sun and any star's core. And electromagnetic radiation travels through space in the form of waves. So you have an animation here, and you can see that we call it electromagnetic radiation because it has properties in both the electric field as well as the magnetic field. So you can see that we have both of those words here in electromagnetic radiation. So a couple of properties of waves. You will get to know these much better in physical science next year, but you do need to have some basic understanding of them now. So the distance between the crest of one wave and the crest of the very next wave is called the wave length. Makes sense, right? It's the length between two waves. So we can have waves that have very, very short wavelength, which means there's not much length between them. There's short length between the waves. Or we can have longer wavelengths, which means there are longer lengths between the waves. Now, I want you to think about this being at the beach. So if you are at the beach and there is a short wavelength, it means that you have waves coming on shore very, very rapidly. Okay, that has more energy than a day at the beach where there's a long wavelength. Okay, you can see just based on the way I'm moving my hands that short wavelength has a lot more energy than long wavelengths. Okay, so we also say that short wavelengths have a higher frequency, okay, or higher energy, and longer wavelengths have a lower frequency or a lower energy. So electromagnetic radiation, all electromagnetic radiation travels at the speed of light in a vacuum. Space is considered to be a vacuum. Roughly that translates to 300 million meters per second. Okay, so it's really, really fast. It's 186,000 miles per second. And it also means that the Earth receives light from the sun 8 minutes after it leaves. So what always kind of blows my mind is that we live 8 minutes away traveling at the speed of light, the fastest thing we know in the universe. It still takes it 8 minutes to reach Earth. So some characteristics of waves and the electromagnetic spectrum. So the electromagnetic spectrum, which we often shorten to just be the EMS, consists of the complete range of electromagnetic radiation that is emitted by the sun, and it's placed in order of increasing energy. Okay, so I want you to notice. So long wavelength, low energy is going to be radio waves. The next jump up is microwaves, followed by infrared and visible light. So this is the teeny tiny part of the electromagnetic spectrum that we are able to see, that our eyes are detectors for. It sits right in the middle. After that, we have ultraviolet, X-rays, and gamma rays. So kind of a rule of thumb to think about the energy, anything that is visible light and below or lower energy than visible light is safe for us. It doesn't cause us harm. Anything that is above visible light has too much energy for our bodies and can cause us harm. So ultraviolet light can cause sunburns. X-rays, this is the reason that they put the lead vest over your body. It's also the same reason they ask all women, are you or could you potentially be pregnant before they take an X-ray? And then gamma rays are often used in very, very tiny doses to treat cancer. And we're going to talk about that in just a couple of minutes. So, rule of thumb, visible light and below is safe for us. Above visible light can cause us harm. And that has to do with the amount of energy those waves are carrying and what it can do to our cells when our cells encounter that energy. So you've actually already seen this video. I'm going to skip it. So here's a quick skills check. So what are the lowest energy waves of the electromagnetic spectrum called? You should have guessed radio waves. Okay, lowest energy. How about the highest energy waves? So it's got to be the opposite from radio. Good job. Those are gamma rays. It's the same thing that made the Hulk too. Okay. What part of the EMS is detected by the human eye? Excellent. The visible light. So then now, what is the lowest energy color in the visible spectrum? So here's your visible light. And remember that we have things arranged from lowest energy to highest energy. So we want to pick the color that is furthest to the left, which is red. Now I want you to notice something. What comes just before the red color on the EMS? Infrared. So then what's the highest energy color in the visible light spectrum? That's right, it's violet. And look here, what's the next thing up from visible light? Ultraviolet. So then which one travels faster in space, radio waves or gamma rays? You sure? You're positive? It's a trick question. They both travel at the same speed. Remember, radio waves, microwaves, infrared waves, visible light waves, ultraviolet rays, X-rays, and gamma rays all travel at the same speed. They all travel at the speed of light. So you should have a chart on your note that you are going to be filling out as we go through some of this information. So radio waves have the longest wavelengths. They're about the size of a football field. So it means that they're very low energy. We often use them as broadcast signals for radio broadcast, television broadcast, and some of the older cell phones also use them. These days we use the next level up for cell phones, which is microwave. But radio waves are also given off by stars, galaxies, and comets in space. So here's an interesting video about how your radio actually works. Have you ever thought why there's AM and FM, and why if you're trying to tune it, sometimes it's fuzzy and sometimes it's not? Here's the answer.
Radio waves are part of the electromagnetic spectrum, which also includes X-rays and visible light. Generation of radio waves uses the relationship between electricity and magnetism. If an electric battery and a magnetic compass are joined in a circuit, whenever you complete the circuit, the compass needle moves. The magnetic field that has been created can also be detected in another circuit placed near to the first. This is how radio waves travel across space. With powerful transmitters, they are sent very long distances and picked up by an aerial on the receiver. To send complex signals, a sine wave can be used, which is continuously changed through modulation. The height or amplitude of the wave can be varied, or its frequency, the number of wave crests per second, which is counted in hertz. The varying pattern carries the message. The wavelength is the distance between wave crests and is typically hundreds of meters for radio waves. But the frequency is millions of waves per second because radio travels at the speed of light. There are very many radio waves all around us, so a receiver must have a tuner in order to isolate a particular signal, as well as an amplifier to make it stronger. Modern digital radio breaks the signal into pieces coded as numbers, which are reassembled into sound at the receiver. They are transmitted across much wider frequency bands than analog radio. This gives a more reliable signal, and it means that one digital signal can carry many programs at the same time. Radio frequency bands are allocated for different purposes. Television, for example, uses higher frequencies than radio broadcasting. ITU is where international agreements are made about allocating frequencies for the many services that use radio today, including mobile phones and other devices.
So there is a bit of a question if we are going to run out of radio wave frequency because of the cell phones and then the number of satellites that are going up that use radio frequency, in addition to all of our traditional AM and FM radio stations. So if you want to learn more about that, you can Google it. Will we run out of radio frequencies? Okay, so the next level up on the electromagnetic spectrum is microwaves. These can be measured in inches to feet. And microwave energy is able to penetrate haze, light rain, snow, clouds, smoke, which makes it awesome to use with weather forecasting. You may have seen some of these big microwave transmitters and receivers. The one that I can think of is off I-4 if you're up towards Altamont. It's one of the Doppler weather stations, and you can see these big microwave drums. There also is an enormous microwave tower in Key Largo, if you've ever been down to the Florida Keys. It's that thing that sits many stories higher than everything else around. That's an old microwave tower. Microwaves are also what's used for radar when the police radar guns are used to catch you speeding or catch your parents speeding, because I know you guys won't ever speed when you learn how to drive. And then also for cooking. So a microwave oven produces microwaves, and it is the microwave that actually interacts with the water particles in your food that helps heat it up. All right, so the next one up, so we're getting higher energy with each step, is infrared waves. You experience this with the heat lamp. So the wavelength, you can tell we're getting much smaller. We can be from the size of a pinhead to the size of a cell. We experience long infrared waves as heat. So that's why I said the heat lamp. The short infrared waves are used in TV remotes and infrared cameras, like the picture of the cat. So the hottest part is going to be the brightest part, and you can see the temperature scale over here. So the white is always going to be the hottest, and the dark purple is always going to be the coldest. There used to be one of these when you came off one of the Disney rides. At Epcot. I don't remember if it was Spaceship Earth or if it's Test Track. But if you stand in front of it and you put your arms out, what do you think are going to be the hottest parts of your body? Yes, so your heart area and your brain, although that is behind a protective skull, but your armpits are the other ones that will also glow bright white. And the pit viper family of snakes actually see using specialized organs to detect infrared. So although they have eyes that see visible light, they also have this extra characteristic, this extra special adaptation where they are able to see in infrared. And that's one of the reasons that they're such good hunters. And you can't really hide from infrared because it's sensing the heat. Visible light. So this is the one that we experience the world with. If you can see it, it's visible light. Our detectors, our eyes, are fine-tuned to a very, very small part of the electromagnetic spectrum. The wavelength is about bacteria-sized, and then we see these waves as the colors of the rainbow. Each color has a different wavelength, which you can see really nicely in this image. So red has the longest wavelength, so it's going to be the lowest energy color. That is why, like on naval ships, they will use red lights. They're less likely to be picked up. They're not sending a great big beacon that says, hey, we're here, come visit. Violet is the shortest wavelength or the highest energy. So remember, infrared is on one side and ultraviolet is on the other. When all of the waves are together, it produces white light. And we are going to look through spectroscopes in the coming days where you will put basically white light in, but it will produce and separate everything into the colors of the rainbow for you, like a prism does. All right, ultraviolet waves is the step above our visible light. The wavelength is about DNA size, so we're really starting to come down in size. We cannot see ultraviolet, but we can experience it as sunburn. We do have the black light bulbs, which you experienced with the EMS lab. But we can use UV to kill germs. In forensics, it can be used to detect body fluid, which is what they are showing you on this gentleman's hand here. And then it can also be used to detect counterfeit money. So if you have a UV light at home and you have fake money, which hopefully you don't, you end up with this kind of bleed of the UV bar or no UV bar at all. Whereas for real money, you should have one straight UV bar. So sometimes you'll see the cashiers, if you're using a big bill, they have to write on it and shine what looks like a flashlight. It's not just a regular flashlight. It's actually a UV light that they are looking for specific things. And I think a lot of driver's licenses have these in the background now. And again, it's a way to help prevent counterfeit because this is not easy to replicate. So this is always really cool to me. So this image on the left is what we see in visible light. So this is a black-eyed Susan. It is the state flower of of Maryland. But this is what an insect actually sees. And then here's another one. This is what we see, but this is what an insect sees. So why do you think many insects actually see in UV? What does this look like? It looks like bullseyes. the bullseyes are bringing them right down into the pollen. So many insects do not see visible light the way we do. They're actually seeing in UV, and flowers have adapted a way that they truly look like bullseyes for insects, kind of attracting them. Hey, come pollinate me. All right, X-rays we're getting real high. They are a high energy form of electromagnetic radiation. Wavelength is about the size of an atom. Frequently, we're using them in medical settings because they pass through soft tissue, but they're stopped by denser bone tissue. So you've got a couple of X-rays here. It looks like a sewing needle. Ouch. This is a pneumonia in the lung. You can see that this lung is very clear, whereas this one is surely showing signs of infection. And here's my favorite one. You really didn't know where the keys went. Like, you're looking all over in the purse, in the car, and the dog swallowed them. Obviously, this is a huge issue for the dog. They've got to get them out surgically before it perforates a bowel or anything. And interestingly, X-rays are emitted by black holes and by supernova remnants, as well as by the sun. So by studying black holes, by studying X-rays, we're actually able to see things that we're not going to be able to see in visible light. And then last but not least are gamma rays or gamma waves. They are the smallest, they have the most energy. We're talking about wavelength the size of an atomic nucleus. Now keep in mind, for wavelength size for radio waves, I said that they're about the size of a football field. So you can think about how much smaller those wavelengths are, and you can kind of start to process the changes in the amount of energy that it's carrying. Gamma rays are generated by radioactive atoms and during nuclear explosions. And gamma rays can kill living cells. If you are familiar or know somebody who has ever had a radiation therapy for cancer, it is actually using minuscule doses of gamma rays in very specified locations to hopefully kill those cancer cells while leaving as much as the surrounding tissue undamaged. I've always thought that this was a really cool image of the Crab Nebula. So here's what we see in visible light. It's beautiful, but it's just kind of dusty. But then once we start looking at it in gamma rays, we can see that there are areas of high activity with gamma rays within the Crab Nebula that are completely blocked to us in visible light. All right, so does all of the sun's radiation reach Earth? You should be able to look at this picture and figure out no. The same way some materials in our lab transmitted and some blocked, our atmosphere does the same thing. So things that are stopped or absorbed by Earth's atmosphere, we can see that gamma rays, thank God. X-rays, thank goodness. Most UV, okay, we still get some UV that comes through, and that's why we get sunburn. But look how much worse it could be. Visible light does come all the way down. Infrared does come all the way down. That's why you can feel the heat of the sun on your face on a hot day. Most microwaves are blocked, but most radio waves are transmitted. So I just kind of answered that, which pass through. So then why do we have to put certain telescopes in space? Why on earth can I have radio telescopes and mostly optical telescopes, but everything else, if I want to study it, I've got to put it all the way up there? Okay, so we've got Fermi, which is a gamma ray observatory. Chandra is the X-ray observatory. Spitzer was kind of in that low infrared between microwave and IR. Okay, if you said it's because those waves don't reach Earth's surface, you're exactly right. I can't put a gamma ray telescope on Earth's surface. I'm not going to get any data. My atmosphere is going to completely block it out. So studying all types of electromagnetic radiation is important because it gives us a much better view of what is out there. There's an entire invisible universe there that we can study with the right receivers. But if we're only using radio telescopes or only using visible light, it means that we're missing out on all of this incredible information that the cosmos is giving us in other parts of the electromagnetic spectrum. So here are some different pictures of the Milky Way galaxy using different frequencies. So you can see one's infrared or far infrared. This one's closer to the ultraviolet, or closer to violet, I should say. Mid-infrared, near infrared. This is visible. This is X-ray, and this is gamma ray. And you can see that when we start combining these images, we get a much clearer picture of what's happening out there. All right, so that's the end of this slideshow. Hope you enjoyed. There are some module pages. There are some module pages that will be open that you can click through and learn more about the different parts of the electromagnetic spectrum if you are interested. Bye guys, have a great day and an awesome weekend.